Okay, here we are, heat and temperature calculations for LCPhysics, new specification. These are all calculation questions about specific heat capacity, latent heat, and also U values. The problems will always be different we do in physics, but what we have to do is develop our problem solving skills and approach them the same way every time. So we're going to read these, write out what we have, and then write out what we have to find. What we're going to use is this graph method. G is for given, what is given, or what we require. A, analyze, what equation do we need. S, solve, and the last S is sense. Does it make sense? Let's apply this problem solving to question 1. A copper block of mass 2.5 kilograms. So mass M is 2.5, and that unit is correct, that's good. Is heated from 20 degrees to 85 degrees. So they're giving us a change in temperature, a delta theta. The temperature is changing from 20 to 85. So our temperature change is 65 degrees. And they also give us the specific heat capacity of copper, that's C, is 385. So we have got what is given, done. All those numbers we have used and noted down. Next step, what is required? What is required is the heat energy absorbed. So we're looking for what is Q, and we write that down as well. Write down what it is so you can link it to your equation. Now we have Q, C, M, change in temperature, so we can use our formula for specific heat capacity. All right, the heat energy absorbed, that is Q. Let's rearrange. Q, let's write down here. Q is equal to MC and delta T, change in temperature. We can use this symbol as well for change in temperature. Our mass is 2.5. Let's zoom in to make this neater. How do I change the size of this? Here we go. Q is equal to 2.5 multiplied by C, which is 385 by our change in temperature, 65. All we get for that is 62.56, or 62,562.5. We can write that in a cleaner way. 62, if we bring in our decimal point, 1, 2, 3 places, that's 62.56 by 10 to the 3, but by 10 to the 3 just means kilo. Kilo and what? Kilo bananas, what's our unit? Meters. It's energy. Q is energy, so that is joules. So 62.56 kilojoules. Final answer. There we go. If this energy was supplied by an electric heater of power 750 watts, how long would the heating process take place? So we're going to use our same method again. What is given? What is required? What's the formula we need? So let's go. What is given? We have given the power. The power is equal to 750 watts. How long would the heating process take place? So what do I need? I need time. And then we need to analyze what equation would be good here. Well, we need an equation that has power and time. Power is equal to energy divided by time. So power is the rate of energy transfer, how quickly energy is given from one place to another. We have got power. Tick, it's 750. Energy, do we have energy? Yes, we do. We just found out what the energy was. Q and E are the same thing. We just use Q if it's heat, but it's still joules. Joules is joules. So we have energy. That means we can find time. We just need to rearrange. Temperature is equal to energy divided by power, or time. Time is equal to energy. Energy is 62.56. Or let's be more accurate, let's put the whole thing that we got. 62562.5. 62562.5 divided by power, which is 750. That means our time is 83.42. And then here's the question, what are the units? Time could be in seconds, minutes, or hours. This goes back to our definition of what power is. Power is, let's do this in black. Power is the amount of energy transferred per second. So its unit is watts, but watts actually mean energy per second. They mean the amount of joules per second. So if I have got joules in here, and I've got watts in here, and I have joules and watts, that means this must be seconds. So this is 83.42 seconds. Let's see if that makes sense then. 80 seconds. This is for a copper block to be heated from 20 degrees to 85 degrees. So to change 60 degrees, could it take a minute and a half? Seems kind of reasonable. It doesn't seem crazy. If it was something like, 40 minutes or 50 minutes or something really small like a second, then you could think back and be like, I don't think this is right. That is problem 1 done. Problem 2.